All right, thank you very much. Today I'll be talking about the Grasshopper problem, which is a unique problem with some interesting connections to quantum information theory or quantum cryptography and statistical physics. To start off, we'll look at a shared 2-qubit state, singlet state between Alice and Bob. And Alice and Bob's goal here is to measure this, their 2 qubits to see if the correlations that they measure are in fact quantum or instead classical due to some interference by an outside party like Eve. And so in certain cases, or certain methods such as CSSH and Caves-Bronstein, Alice and Bob will have a fixed set of measurements they can make on their qubits. In the case of CSSH, they can measure, they each have 2 bases they can measure in, and then Caves-Bronstein, they each have n finite bases they can measure in. And instead, we want to increase the efficiency of their classification by increasing the randomness that they can introduce in the problem by allowing them to measure in any given basis on the one stipulation that their measurements have to be at an angle theta from each other, as indicated there. Looking at we now want to look at the local hidden model variable equivalent of this. And we can see here, we traded out our 2 qubits instead for 2 colored spheres, in which are inverses of each other. So we can see on the left here, if see this button, Alice were to measure here, she'd measure green, and Bob would measure an angle theta to it, and we'd find we measure at state white. And these colorings are ones that maximize the anti-correlations of their measurements. And so now the question is, how do we find these local hidden variable models? Well, consider the Grasshopper. So we start off by putting we cover half the surface of the sphere in a wand, such that for every single point on the wand, the antipodal point is not on the wand. And so you can see wand here, not wand here. From here, a Grasshopper will randomly land on this lawn and then jump at a set angle theta away in a random direction. And the question is, what shape of wand will maximize the probability of this Grasshopper landing on the wand? I will want to clarify that there is no need for this wand to be contiguous. The only property it needs to have is that it meets the first antipodal condition we described above. And so this is a very hard problem to solve, as there's an infinite number of wands you can create, and it's probably impossible to solve analytically. So we're going to simplify this problem by discretizing it. And so now we want to introduce this tiling on a sphere, which also introduces its own problems, because there are no such thing as a uniform tiling on a sphere past the Platonic solid. So we want to choose some properties that our sphere will have, our tiling. So we want to make sure that it has the antipodal condition, which is the entire point of the problem, as well as we want each spin or each point on the sphere to have approximately the same area. From here, we can kind of simplify this problem more by cutting the sphere in half and looking at each of these pairs of points as a single spin, where the direction of the spin indicates where the wand is located, which antipodal point will this wand be located on. And then we can describe the probabilities associated with them with interactions between other spins. So spins that are the correct distance away, theta, will interact with each other dependent upon if their spins align or disalign. And their alignment requirements are dependent on the distance between them and where they're located. So a point on the top. Oh, sorry, slipping down. So we've somewhat created an Ising model, which has the unique property of being, instead of looking at nearest neighbor interactions, we're now looking at interactions between neighbors that are a fixed distance theta away. And so if we want to check to see how our grid performs, we can see here, we compare it to the analytical solution for a hemispherical wand, and we see it matches actually quite well, with the caveat that at the extremes where there are not that many interactions between spins, the non-uniformity of the grid starts to introduce some errors, but in this case, we have large enough grid size to where these errors are averaged out. And so from here, we can now start on actually optimizing our wand shape. And we do so by using a heuristic known as simulated annealing. And this is a Monte Carlo Markov chain, which allows us to introduce this artificial temperature T that controls how we search through this space. And so we can imagine we start off with some configuration, and we want to propose a change to this configuration. And we want to see, okay, well, does this increase or decrease the probability? If it increases the probability, great. We made a good change, and we want to accept it. However, if it decreases the probability, we can still accept this change upon as a function of 2 parameters. First is the artificial temperature T that we've introduced. We're at high temperatures. We are able to make a lot of different changes. We have the energy to spare to make suboptimal changes. And the other parameter we want to look at is just how bad of a change it was. So If it was a really bad change, we're not going to want to accept it. And we can see as we search through this space, at high temperatures, we're going to rapidly search through this space because we're accepting just about any change. But as we make more and more changes, we're decreasing this temperature, and now we're going to start slowing down. We're going to converge to this local maximum, and hopefully, if we're lucky, we find the global maximum. Now that we've done this, we can actually see the fruits of our labors, and we can see the results, the different lawn shapes that we've created. And starting from here, we can see at low jump distances, we're going to have what we call these cogwheel shapes. It's important to note that these cogwheels always have an odd number of teeth, given that for antipodal condition, every point that's a cog, like a tooth of the cog, has to have the opposite point not being a tooth. But as we increase this jump distance, we're going to find that these cogs decrease in number, but increase in size. And then we approach what we call a critical angle here. Oh, sorry. Trying to critical. Oh. At about pi over 2, we're going to find that we're at this critical angle, in which case the grasshopper can jump to any point, and that point that it can jump to also can jump to its antipodal point. So for any configuration of this wand, we're going to have a probability of 0.5. So each one's equivalent. But as we're around this critical angle, we're going to find that we create these labyrinth type shapes. And these shapes increase in complexity and tightness as we get closer and closer to this critical angle. But moving past this, we get the shape I like to call the oracle. I don't know why. It looks like a flying eye to me. We get some stars and then some stripes, where this number of stripes and the thickness of them changes with the angle as well. And then we approach another critical angle at pi, in which case the grasshopper would jump directly to its antipodal point. So every probable line is equally terrible. But we also see the labyrinth shape here. And so we can plot our results, like how well the optimal wand performs to the hemispherical wand, as well as just kind of delineate where these regimes are. So we start off here with the low jump angles pretty close to the hemispherical wand with cogwheels. Then we introduce the labyrinth regime as we approach this critical angle here at pi over 2. We have our stars, stripes, and oracles. And then again, we're going to keep increasing as we get into this labyrinth regime. And keep in mind, at pi, the probability is going to be 0. It's going to plummet straight down. We can also look at our wand shapes in a different light, and one that allows us to kind of see more clearly why these shapes emerge. And so here I'm plotting how important a spin is to this configuration. And by that I mean you can see towards the edge of this wand, we're going to have less important spins. That means if I were to change any of these spins, I'm not going to be changing the probability too much. It's not that big a deal, because at this point, on the edge, the grasshopper is most likely to jump outside the wand. But towards the center, we can see that we have the most important points, and that makes sense. That's where the grasshopper is most likely to remain on the wand after jumping. And this provides some interesting insight that we originally can't see at surface value, because at face value, these two shapes don't seem to have any similarities at all, but we can kind of see why the star starts to emerge as we increase the jump distance here. And so these two shapes that had apparently nothing to do with each other are actually somewhat related, and it allows us to, I guess, get a greater insight to the shapes that we're producing. From here, I want to talk about a little bit about we've also done this grasshopper problem on other geometries, and if you're interested in finding out more about this, feel free to check out our YouTube channel here listed below, Grasshopper Media, where we discuss the grasshopper problem on the planar surface, in which case the grasshopper is no longer confined to this antipodal condition and is now on the surface of the plane, as well as we look at how this grasshopper would perform in now flat 3D space and how that would look. But thank you for your time. Let me know if you have any questions. And if you want to talk to me after the fact, please do so.